Hello and welcome to a new repair video. Now this one's going to be a little bit different because I'm actually in my dad's shack, and the radio that I'm trying to repair is his Argonaut V from TenTec. Now the reason why this is going to be a little bit different is that he's got like lots of old gear in his shack that I'm going to use to try to repair this. So be prepared for things looking a little bit different than usual. Now this radio here is a shortwave ham radio. It works on all shortwave bands, and it's got a fairly nice receiver built in, which actually works. If I turn up the volume here, you hear the noise, and we tested this on the antenna. This works nicely. Now the part that does not work is the transmitter. I've got it set to CW mode here, and if I take the microphone here and hit the PTT, you can probably hear the CW side tone, but if you watch the display here, it's not putting out any power at all. It's not doing that on any band and any mode, so there is really no way to get any output power from this machine. I hooked up a dummy load, of course, to this box, and also a SWR, well actually it's a tuner, and let me focus here on the tuner here. It's got an output power display here to verify that there really is no output power, but as you can see, the dial is not moving at all, or just barely moving, so clearly there is a problem here. So let's have a look at the documentation that is available from TenTec, try to understand how this radio works and what could be wrong. The good news is that this radio comes with a fairly nice user manual that contains, in addition to, of course, instructions on how to use the radio, also information on how the radio works, schematics and things like that. But the service manual, and that's the bad news, the service manual is not available. Things that you typically find in the service manual, like information on what voltages and signal levels you can expect on various points in the circuit, that's not available. So I took the user manual and put together a kind of block diagram on how the transmit path in this radio works. Let's start here. There is a microphone, of course, and a microphone amplifier, and the signal from the microphone is digitized. So there is interesting things going on in the digital domain here in this DSP, which is basically depending on the mode, be it FM or USB or AM or whatever, a low frequency modulated signal is outputted here at this ADC. So the actual modulation of your voice that enters the microphone here happens in the digital domain here inside this DSP, which is maybe, I'd say usual in more modern radios, but the kind of old school traditional way of doing things is certainly not like that. So anyway, if you're working in CW without any microphone input, of course, this part here is turned off and it's just synthesizing a carrier at around about 14 kilohertz or so. And that also holds true for if you're using a phone mode. There is the modulation here is at 14 kilohertz, and then up converted using this mixer here to 450 kilohertz. Now this part here is on the logic board. There is 3 boards inside the unit, and the first one is the logic board that contains a microcontrollers and DSPs, and also handles kind of the low frequency stuff here. Then there is a large RF board here that does all the RF signal conversion, and there is also a final PA board that amplifies the signal and sends it to the antenna jack. So that's kind of the high-level overview, and at the output of the logic board here you get this 450 kilohertz signal here. That then goes into a ceramic filter because as usual there is 2 output frequencies here, at the output of that mixer, so one is filtered out, and then it goes into a second mixer that has an IF of 45 megahertz, which is then amplified. There is an attenuator here that is programmable, and then there is a third mixer here that essentially outputs the final synthesized waveform that is then just filtered, amplified, filtered a bit more, and sent to the antenna. Now, in case there is no output power in a radio, the power amplifier is kind of the first thing that pops into mind, because often these break because these are kind of high power circuitries, and you know, there is lots of things that can go wrong. Maybe you forgot to connect an antenna, and then you're overloading the amplifier stage here and things like that. So anyway, so I spent a considerable amount of time debugging this, and so the signal that gets in here, and I'll demonstrate that in a second, the signal that is getting into this power amplifier final board is maybe 45 milliwatts or so. Now that is kind of low, but it's not, you know, like dramatically low. So so for quite some time now I've tried to debug this and check why at 45 milliwatts in I'm not getting the 20 watts out that I should, and I sort of came to the conclusion that the power amplifier is working fine, because I can't find any problem. There is a bunch of documented issues that deals with a filter bank and the diode switching here. But that seems to work fine, so so that's not it. Also, these problems typically happen on just one band and not all of them, so I sort of managed to rule that out, but I'm still not quite sure what's wrong. This still remains a possibility. I'm not quite sure that the PA is fully working, but I found something else that is interesting. Now, some other things I checked was there is a directional coupler here that is coupling out the forward power and the reflected power. Now, one thing the radio could do is fail to measure that there is no reflected output power, and decide that there is high SWR and reduce the output power. But I checked, and that's fine, and that voltage here gets digitized fine. That is the one that is coupled out here. So that is not the case. Also, I'm not quite sure how this radio actually does set the output power. There is a knob, a potentiometer at the front plate for the output power, and that is just digitized, and I'm not quite sure what's happening with that because this is handled in software. Something I could imagine is that this is playing with that variable attenuator here, attenuating the signal more or less depending on what output power is measuring here, and with a control loop then trying to match the set point of the output power. That is one possibility, or it might do the same just inside the DSP, synthesizing a waveform of some amplitude to match the output power. So anyway, but that is not the case. The power potentiometer works fine, and also the reflected power is coupled out fine and digitized fine, so I don't think that is the problem. There is also a bit of circuitry to do that control loop kind of thing, but that seems to work fine, so that's not it. So let me show you first the measurement I did here, because that is a very important stage. Usually when dealing with that, you want to figure out whether your fault is here on that board, or on that board. And in this case, I am not quite sure. I'll show you the measurement I did to try to rule out that it is on that board, but that is a bit inconclusive, as I said. And then I'll show you some more things that happened around here, which I find a bit weird. So first, I'll check the connection between that output filter here and that first transistor amplifier, because there is a coaxial cable here that I can disconnect and hook it up to some measurement instruments to figure out what's going on there. Okay, so that's the inside of the radio here, and the board here at the top is the RF board. Now, if you remember my diagram that I just showed, this little guy here, well, let's actually use that. I said that there is a 14 kilohertz signal here coming out of this ADC, and that is up converted here to 450 kilohertz. That's because we have a 450 kilohertz filter here. So basically that 450 kilohertz signal here enters through that connector here, and that guy here is the 450 kilohertz ceramic filter. And then there is a whole lot of circuitry with all those amplifiers and mixers and filters, and in the end the signal is getting out of this board through this connector here, that coaxial cable, and is entering the power amplifier here at the back of the unit. It's mounted at the back because there is like cooling fins here on the back because it's getting quite warm. And you can see the filter bank here with all the filters for the various bands, and the antenna connector here is on that side. So basically that's how it works. So that cable is sort of key, and this is very important when you're attempting a repair with basically any kind of radio, because quite often you'll find an RF section and the power amplifier section separated using some kind of cable. Now you can actually plug that out here, and instead I have a cable that is actually this guy here. One end looks like that, so that's exactly the same kind of connector that you'll find in many radios. Actually, it's not only TenTec, it's also, I've seen them in Yaesu radios, and Elecraft I think also uses them. I'm not quite sure how they're called, but it really pays off to have a cable with one of those guys at the end, because then you can just plug this in here. And at the other end of that cable I have this guy here. Now that is not the nicest way of doing this, but basically this is a BNC 3-terminal connector here, and I'm hooking up that probe that I just showed here on one end, and that is just a 50 ohms terminator here, and that goes here to the other end. And that guy here goes into the scope, so I have this terminated kind of close to the end with a 50 ohms, and I'm able to take a voltage measurement here with this cable terminated into 50 ohms. So let's do that and see what we get. Okay, now so this is where it's getting really old school, because that's a very old scope and not the greatest 20 megahertz of bandwidth, but still it does the job. You can actually see how much my dad had to pay for this guy here. He picked it up at some ham radio flea market or something. But anyway, so there we go. So I've got this 50 ohms termination T thing here, kind of hooked into channel number 1. And if I key the microphone, or the radio rather, I get this waveform. So because I don't want to kind of key this all the time while I'm talking, I'll try to capture that. Nice. Okay, so now what we're getting here is a waveform that does have the 2 megahertz. This radio is set to 2 megahertz pretty much, and it's got the 2 megahertz waveform here. That's nice, and also it has about 1.5 volts peak to peak, so that's around about 45 milliwatts or so in terms of power. Now that, as I said at the beginning, that seems to be kind of low. But it might also be just fine, and because I don't have the service manual, I'm not quite sure. But the output that I'm measuring at the antenna jack of the radio, remember that this is not the antenna jack, that's like the input to the power amplifier. The signal that I'm measuring there looks fine, and that's sort of indicating that it's not a transistor that went bad or something like that. Also, the radio is barely drawing any more power while transmitting than when receiving, which is also another indication that it's just not putting out any power, but the power amplifier itself seems to be fine. Now there is many things that could still be wrong, and I spent quite some time checking them, and it seems to be fine. Maybe I'm just wrong on that, but after I realized that things seem to look fine, I started to look at a few other things, and I found something that was really weird. So I think I'll show you that other issue that I found, and we'll try to debug that one further before I get back to the power amplifier, because while there is still a chance that the power amplifier is bad, honestly, to me, it doesn't look like it. So I'd rather check out that other problem and see what we get there. Okay, so we're back at the schematic, and the part that we're looking at is actually the section over here. An ADC, a switching mixer, and an amplifier. And in the actual schematic, things look a bit strange, but the ADC is actually this guy here, no problems, and the switching mixer is that guy here. Now this is drawn in a weird way, but all this does is just hooking up and turning around both inputs, because the ADC is synthesizing a balanced signal. So this is symmetric, and then it's very easy to implement the switching mixer, because you just take the two inputs and at the LO frequency you swap them around, and that's all this part here does. And then this amplifier here, basically all this guy does is taking this balanced signal here and converting it to an unbalanced signal here at the output. So in a way it's kind of a balun implemented with an operational amplifier here. This whole thing here runs at 450 kilohertz, so that's not that high a frequency. And as you can see, there is a 1.5K resistor here at the output, and that then goes into the connector that I showed you that connects to the RF board. And at the input of the RF board, that's this guy here, at the input at the RF board, this goes straight into a 450 kilohertz ceramic filter. And usually from experience, I know that these guys have an input impedance of about anywhere between 1 and 2K. So this really looks like some sort of impedance match here with a 1.5K. And interestingly, I measured a clean signal that contained exactly what it should here essentially not the output of the operational amplifier, but after that resistor, because I don't have easy access to the operational amplifier output. So, but if I measure that guy here, I only get about 400 millivolts peak to peak, which is kind of weird, especially if I look at this ADC here. I'm able to measure like 300 millivolts peak to peak through a via. I have to say that the logic board is not accessible from the top of the unit, because the RF board and a metal shield is in between. So I had to turn around the whole unit, and then through a via I can measure 300 millivolts peak to peak here. And because this is balanced, I'm assuming 600 millivolts peak to peak of the total signal here. And then somehow this gets reduced to 40 millivolts peak to peak, which is really strange, because if you consider that the ceramic filter should have a 1.5K roughly of input impedance, there should be a voltage divider here of half. So I'm not quite sure why I'm getting the 40 millivolts peak to peak. So let me show you that measurement, and then another one, and then let's discuss what could be wrong. Okay, so that's again the inside of the unit here, and the 450 kilohertz signal is coming through that connector here into this crystal filter. Now what I will do is I will take this old school scope probe here and just measure what I'm getting here through that connector here. Okay, so now I've got the probe set up exactly like I showed you before, and I'll take the speaker mic again and key the radio. And you can probably hear the side tone and also see that output waveform here. Now unfortunately I can't reach over to the scope and freeze the screen, but note two things here. First, this is about 1 division peak to peak, And second, this looks nice, the frequency is right, and it also looks like exactly what you'd get from the output of that switching mixer here. It's just very low in amplitude because I've got the scope set up to 2 millivolts per division, and it's a 10x probe, so that's 20 millivolts. It's not even the 40 millivolts I talked about before, it's 20 millivolts peak to peak. So something seems to be really wrong here, because the ADC has an output of 300 millivolts peak to peak, or 600 rather, because it's balanced. And there is no way that switching mixer can be that bad. I mean, we're basically losing everything here, and also the operational amplifier should have unity gain. So basically, at the output here, we're getting a very low signal. Okay, so now I'm starting to think that something is wrong either with that switching mixer, the operational amplifier, or that crystal filter here. It's not the ADC, because I measured the ADC voltage at 300 millivolt peak to peak, no problem there. But there is one more thing I can do before I start messing with the circuit, and that is, let's check the voltage here that I have at the input of the crystal filter, and that is 80 millivolts. So that is fairly low, because the operational amplifier should give me a half rail output when I'm not transmitting, and that's 5 volts. So somehow more than 4.9 volts of the 5 volts here are dropped across that 1.5K resistor, which seems to be quite high. Another thing I can do is turn off the radio and set the meter to ohms and measure the resistance here at that point. The negative lead of the meter is hooked to chassis ground, and I'm getting 25 ohms. That is very, very low, and I don't think that the ceramic filter actually should have that low ADC resistance. So let's summarize what we got here. We know that we have a decent output signal from the ADC. I haven't shown you that measurement, but because it's quite tricky to do measuring through that via, but that is nice. And we know that we've got a very low signal here at the output of this circuitry. So something might go bad, either inside the switching mixer. There is no way this switching mixer can be that bad if it's operational. I mean, switching mixer have actually quite a nice conversion gain, so I don't think that should be the case. And also, this operational amplifier here should have unity gain, so we should not lose anything at all. And then with 1.5K nominal input impedance of the crystal filter that is hooked to that output here, we should see maybe 2.5 volts or so at the output, but that is not the case. And also the peak-to-peak level of the output waveform seems to be very, very low. So what I'd like to do is I'd like to probe that point here, because if that point here, let's say when I'm not transmitting, is at half of the rail, I know that this stuff here is fine, and there is just something pulling down that node here, and that would be the crystal filter. So that would indicate that the crystal filter is bad. So let me do that, and let's discuss then what we can do about it. Okay, so this shows you why this is kind of tricky to take that measurement here. I now took off the RF board that you saw before here. So that's the RF board that was lying here on top of that, and also in between there was like this aluminum kind of shield bracket thing. So unfortunately it is kind of difficult to reach in down to that logic board. So basically what I did is I took a piece of wire here and soldered it to the other end of that resistor here. So basically that would then go to the output of the operational amplifier, or is coming from the output of the operational amplifier, go through that 1.5K resistor, and then to that connector here that you saw before. And I use that wire to compare the output of the operational amplifier to what we measured before at the other end of that resistor. Okay, so now I've got the scope probe hooked up to that wire that I soldered in, and if I take the speaker mic yet again and key the microphone, this is what we get. Now this is the same nice waveform that we would expect. You can actually see the two frequency components that we're getting from the switching mixer there. So that is very nice, and that is also in amplitude 3 divisions. And I've actually have it set to 50 millivolts per division with a 10x probe that is 500 millivolts per division times 3, that's 1.5 volts. So apparently, if I go back to the schematic here, sorry for the poor camera handling here, I somehow apparently have 1.5 volts peak to peak here, but only 40 millivolts peak to peak here. So it really looks like the ceramic filter is loading down the output. Now, one last thing I want to try is measure the voltage, the DC voltage that I have at that point. And I'll switch this back to volts then, and just measure the wire that I soldered in, and I have 5 volts. So that's exactly half of the rail, and this shows me that the operational amplifier is working just fine. So I think what I'll do is I'll try to find a replacement for that ceramic filter and get back to you in the next video. If you have anything to say about this, please share it in the comments, and I say thank you for watching.